All right, so on our balloon here, this is going to represent our Earth, just easier to see with it being it's a yellow balloon instead of using a globe. And I want you to see that there are a couple things I've marked on here, and that would be an N for the North Pole. We've got our equator here, and we have an S for the South Pole. Now what Logan's going to do is he's going to draw us a straight line from the North Pole directly to the equator. Can you do that, Logan?
Yeah.
And remember, we're just drawing a straight line, okay?
Okay.
Here, you take the marker. I'll hold the balloon, okay? So what he's going to show here is if there was no rotation, start up here, start at the end. If there was no rotation on the Earth. Good job. And what he's shown you here is that it's just going to be a straight line from the north to the equator. Now, Logan, I'm going to have you draw, again, a straight line to the equator. And this time I'm going to spin the Earth to show its rotation.
From the end?
Yep, from the end. Good job. Now what I want you to see is that he tried to draw a straight line from the North Pole down to the equator. And what I want you to see is that his straight line is now deflected towards the west. And if we could continue this would have made a clockwise pattern here of how the water is moving on Earth. Now, Logan, I want you to try to draw a straight line from the South Pole to the equator. I'm going to rotate the Earth again for you. All right, and here's Logan's attempt at making a straight line from the south to the equator, and what we can see here is that it's also deflected to the west. But what I want you to notice here is that it's not in a clockwise pattern. From the south, these are going to move counterclockwise, because if we followed his line, it would have went in this direction. From the north, it's going to go in this direction. This is the Coriolis effect, and this is what's going to drive some of our motions of our water on Earth. All right, so that's going to wrap us up for today. What I want us to pay attention to tomorrow.
The Coriolis force is an apparent force that causes air to deflect as it moves over the Earth's surface. Here are two of the main factors that lead to the Coriolis force. Number 1, the movement of an object, and number 2, the rotation of the Earth. Now, regarding the rotation of the Earth, a key factor you need to know is that parts of the Earth are rotating at different speeds. The reason this happens is because the Earth is shaped like a sphere. For example, the circumference or the distance around the Earth at the equator is roughly 24,000 miles. And at 60 degrees north, it's roughly about 12,000 miles. And if we do some math, we will quickly see there is a big difference. For example, 24,000 miles at the equator divided by 24 hours in a day gives us about 1,000 miles per hour. At 60 degrees north, 12,000 miles divided by 24 hours in a day gives us about 500 miles per hour. Clearly a big difference in speed. Since the Earth is spinning faster at the equator, an object that is flying directly north from the equator will gradually be deflected to the right. To have a better idea of how this works, let's look at the Earth from the poles, specifically the North Pole. At the poles, the spherical shape of the Earth looks exactly like a circle, so it's easier to understand. From this perspective, the outer edges represent the equator, and the center represents the North Pole. Now, if you are rotating the circle counterclockwise, which is the direction that the Earth spins, and then place an object from the edge, and then move it towards the center of the circle, you will notice that gradually the object will be deflected to the right. This happens because the edge, which is the equator, is rotating faster than the center, which is the North Pole. Because of this deflection, the Coriolis force plays an important role on the development of typhoons, hurricanes, and the ocean currents. For more videos like this, please subscribe and thanks for watching.